All right, let's talk about properties of matrix multiplication now. Right, this is our next part of matrix algebra. So here we're going to have three matrices, A, B, and C, and we're going to define them to have the appropriate size so that whatever product I write here makes sense. Right, so maybe like, A is n by n, B is n by p, like whatever the situation calls for. Just assume that all the products here are defined. That's basically what we need. Right? And C is just going to be, little c is just going to be a scalar. Right? Then what can we say? Well, one is, what happens if we want to try and multiply together three matrices? Well, it turns out that matrix multiplication is actually associative. So we can multiply them in sort of whatever order we want. Associative. Multiplication. Right? That's good. Now, when I say whatever order we want, like the two that are next to each other, we can multiply in whatever order we want. So A times B first, or B times C first, and then times the third one. Okay. Here, matrix multiplication is distributive. Okay. So this is distributive. Right? But here, I want to sort of emphasize here that this says distributive from the left. Right? And the reason we want to specify that is because, well, it is distributive from the other side as well. And again, it might seem weird that we're specifying, hey, it distributes from the left and right. I'm going to take the easy way out here and just copy this text. Change this to a right. All right. Now we'll see in a second why it's important to point out distribution from the left and the right. It's going to turn out that's actually quite important here. Right. So the last thing is what happens if you multiply a scalar onto this. Well, we can multiply the scalar times the first matrix. All right, so, sorry, what I should be saying here is we can multiply the matrices together first, then the scalar, or we can put the scalar on the first matrix and then multiply the matrices, or we can even put it on the second matrix. Right, this one is kind of an associative property, but I'll not really name this one. All right? So, here we have it. These are some properties here. Let's look at the proof of 3, let's say. All right? So, to prove this, we want to look at we want to start with the matrix A plus B times C. So again, here, remember, A is the matrix Aij, B is the matrix Bij, C is the matrix Cij. Right? So, we need to write out what this is. Now, there's a few steps here in this one. So this is going to be the sum of, well here, let's write down some steps in between so I don't have to just jump right into it. So A plus B is going to be Aij plus Bij, right? Okay. And let's say that A is an A and B are m by n, and C is n by p. Okay? Then A plus B times C, this is going to work out to be A I 1 plus B I, have it to write B I J, C 1 K. Sorry, 1J, I mean. Okay. And then plus AI2 plus BI2, C2J, and so on. To, oops, all the way up to AIN plus BIN, C, and J. All right. So this was the definition of matrix multiplication. It looks a bit weird here since we're dealing with the sum of two things. But hopefully kind of make some sense of this. Right? Now, what we're going to do here is we're going to distribute all of this out inside here. Right? And then we're going to group the things with A's together and the things with B's together. So if we do all the A's, we get AI1 C1J plus AI2 C2J plus all the way up to AIN CNJ. Right? So if we do the first parts of all of these, we get these. Right? And now we'll do the same for B's. So B1 I1 C1J plus BI2 C2J all the way up through BIN CNJ. But look at how these group. Right? So we're going to group these into two pieces. Okay. So here we have AI1 C1J plus AI2 C2J plus dot 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 plus AIN CNJ. Right, that's the first one. Plus, so split it into the second group, BI1 C1J plus BI2 C2J all the way up through BIN CNJ. Okay. But now this first one here, this is exactly A times C. The second one here is exactly B times C. Right, so proving these identities with matrix multiplication is a little more involved, right? We have a little more work to do, but it's fine. It's not the end of the world here. But now, there's something that is sort of missing from this property list. That's quite an important property of matrices that we haven't really touched on yet. And that is, if you think about multiplying two numbers together, you really can do that in whatever order you want, right? However, can you do that when it comes to multiplying matrices? Well, let's find out. So let's say A is the matrix 2, 6, minus 1, minus 3. And B is the matrix 1, 2, 3, 6, let's say. All right? So what happens here? Well, let's say we compute the matrix product AB. Right, so 2, 6, minus 1, minus 3 times 1, 2, 3, 6 Right? So the 1, 1 entry here, remember when we're doing matrix multiplication, we get rows from the first matrix, columns from the second one, and we basically dot product them together. Here we're going to have 2 plus 18, 4 plus 36, -1 minus 9, and -2 minus 18. So we have 20, 40, minus 10, minus 20. Right? So that's the product in this direction. But try this one. Pause the video if you need to. Try out this product in the order BA. Right? We had an example before where, one order the product was defined, the other order it wasn't. So that's already a little suspicious. But let's look at this here, where we can multiply in either order and it makes sense. So if we multiply this out, right, we're going to have 2 minus 2, and then we get 6 minus 6, and then 6 minus 6, and then 18 minus 18. So if we multiply in this order, we get zeros. Okay. So that's a little bit interesting here. So first off, this proves one thing. So AB is not BA, right? What does this tell you? This tells you that matrix multiplication is not commutative. Right? In fact, it's like very not commutative. Right? If we switch the order that we multiply things in, we get two drastically different answers. Right? So that's an important property of this matrix algebra, is matrix multiplication is not at all commutative. Right? And here, there's actually even another problem that shows up, or another wrinkle to this story. We have two matrices that are non-zero, but they multiply together to give us 0. So it's not even true. So it's not true that if we multiply two things and get 0, one of them must be 0. And we saw this with cross products as well. So there's, a lot of things that we sort of lose when that is the case. All right. So we'll end this one here, and then we'll talk about something called the identity matrix coming up.